Hello students, Dr. D again, and this is a practice set for my Chem 1A students at Long Beach City College. In this practice, we're going to tackle the topic of bomb calorimetry. And as you learned in our lecture materials, bomb calorimetry is a technique where you carry out a combustion reaction inside a calibrated calorimeter, and we're able to obtain information about the heat produced by the combustion of a particular substance, and then do other calculations with it. So with that in mind, let's go to our whiteboard and let's carry out this practice. Here is our practice question. Please pause the video for a moment so you can maybe take a screenshot or look at this, have a notepad or a note-taking device somewhere available. And so you can carry along and do the calculations with us. Okay, so here is the question. A 1.000 gram sample of the rocket fuel hydrazine, N2H4, sorry, I couldn't get the subscripts to work here, is burned in a bomb calorimeter. The temperature rises from 24.62 degrees Celsius to 28.16 degrees Celsius. The heat capacity of the calorimeter, including the water, is 5,860 joules per degree Celsius. Calculate the molar heat of combustion of hydrazine in kilojoules per mole. Okay, what I'd like to do is maybe have you stop the video for a moment and think about this, try to understand the experiment, and maybe review what we studied in lecture about this type of technique, and actually build out a strategy for this. Okay, so let's go ahead and get started. Remember that the main purpose of calorimetry is to essentially enclose our system inside a very controlled set of surroundings so that there is no energy exchange with the exterior. So in this case, the surroundings are going to be the calorimeter and the system is going to be the reaction. So let's write that down. Let's go ahead and write that down here just so we have an idea. So we're going to say that our system here is the reaction, which in this case is a combustion reaction. And the surroundings are going to be the calorimeter itself. The calorimeter is built in such a way that it will prevent, or to the best possibility, limit or minimize any exchange of energy with the exterior. And that's what we calibrate it for. So the idea here is that according to the law of conservation of energy, whatever energy transactions happen during this process, there is no net gain or loss of energy. In other words, the energy of the system plus the energy of the surroundings, and actually we want to say not the energy, but the change in energy, will add up to zero because there is no net change in energy. Now, in these kind of cases where we have a limited volume, we are able to say that essentially the energy changes that happen here, since there is no expansion of gases or anything like that that would create work, all of the energy change here is in the form of heat. So we would say that the heat of our chemical reaction, which is our system, plus the heat of our calorimeter would equal to zero. And again, we're saying that this is heat. And remember that when we say heat, heat is an exchange of thermal energy. So what this means, therefore, is that if we rearrange this equation, the heat transacted by our chemical reaction would be minus the heat transacted by the calorimeter. Okay, students, I'm sorry, but as you can probably tell, their recording is being continued after an interruption. I'm sorry, I had some technical problems and some interruptions. So I'm having to pick this up. So the first part of the presentation here you already saw. Let's pick it up where we left off. What we said is that in this system, the heat transacted by the chemical reaction should be equal to minus the heat transacted by the calorimeter. Now, the formula for the heat transaction of the calorimeter is a known formula, and you don't have to memorize it. It will be provided for you in the exam, but it'd be good to have it. So remember, this is minus the heat. This would be something called the heat capacity of the calorimeter times the temperature change in the calorimeter itself. Yeah, these numbers, well, first of all, the heat capacity of the calorimeter, and we can probably write this here. Let's give ourselves a little help here. This is the heat capacity of the calorimeter. And we're going to say that that is going to be equal to what it says up here, 5,860 joules per degree Celsius. So this here will be, oh, I have a little thing in here in the way. Sorry, let me erase these glitches from here. Here we go again. So this will be minus 5,860 joules per degree Celsius. In other words, that is the amount of energy required for the calorimeter to change its temperature by 1 degree Celsius. Now remember that in terms of delta T, don't forget that we always say this is going to be T final minus T initial. And it's important we always define it the same way because that will determine whether the number you get is going to be positive or negative. Okay, in this case, we say that the temperature went from 24.62 degrees to 28.16 degrees. So let's go ahead and write those numbers down here. So let's make sure that I have this in here in the right place. So this is T final. Oops, sorry. Did forget to change the ink here. So this would be 28.16 minus 24.62 degrees Celsius. Always remember to write all the units because this way you'll be able to tell that these numbers here, these units are going to cancel out. Okay, now before we take the next step, and I'm going to let you guys pause the video and do the rest of the calculation, please notice that in this value here, as best as we can tell, there are only 3 sig figs involved. When you do this calculation here, you will have a value that will also limit the number of sig figs. Now, don't forget, because this is a subtraction, you are going to give the result to the proper number of decimal places, not sig figs, but decimal places. So let me have you guys pause the video now and do this calculation and see what you get. Okay, hopefully you have been able to do this calculation here. You will notice that when we do this subtraction here, we had to respect the number of decimal places. This value should be 3.54 degrees Celsius, which means that now when you do a multiplication times this guy, you have 3 sig figs here. Our value of the heat capacity, as best as we can tell, also has only 3 sig figs, which means that the number that we get down here should be technically rounded to 3 sig figs. What is that number? Well, you should have obtained minus 20,744.4 joules. But again, we're saying that only these first 3 significant figures are relevant. Now, we don't have to do the rounding now because most of the time you will have this number already in the memory of your calculator, and we can do all the rounding at the end. So let's leave it there for now. Just keep in mind that whatever we do with this number is only carrying through 3 sig figs. Now, the problem does not end there. This is the heat of the reaction that we carried out. Now, notice this reaction, if we go back to the problem before, was carried out by a 1.00 gram sample of hydrazine. And what they're asking us for is the molar heat of combustion in kilojoules per mole. So somewhere in there, we had to convert what was the heat generated by a 1 gram sample of this compound into kilojoules per mole. Now, obviously, if we had the formula of the compound, whenever we're converting grams to moles, we had to use the molar mass. So make sure that you have available to you our typical periodic table. And again, in the exam, this will be provided for you. So I trust that you are able to find out, based on the formula N2H4, what is the molar mass of hydrazine. Back here to our reaction, we have the number of joules that were generated by 1 gram of the substance. Now remember that at the end of this sequence, what we want to have is we want to have kilojoules per mole. Right now, what we have is minus 20,744.4, understanding. I'm sorry. Hold on a second, let me fix this a little bit here. This doesn't look very good. Let's fix it again. So this is 24.4 joules in a sample that was 1.000 grams. So we need to convert, therefore, joules to kilojoules and grams to moles. So let's start with the joules. Of course, we know the prefixes in the metric system. So we know that 1 kilojoule is 1,000. Sorry, let me fix that a little bit. 1,000 joules. And that will allow us to cancel out the joules and leave kilojoules in the top, which is what we want here on the final result. Now, we need to convert the grams. Of course, grams to moles are converted by saying that, and we should have been able to calculate this, that 1 mole of this compound is 32.06. And that cancels out the grams and leaves in the bottom the units of kilojoules per, moles. So now you should be able to do this calculation. I'm let you guys do it and then come back. Please pause the video and then come back and we'll see what the result is. Okay, so remembering that this number that we brought in here was only allowed to carry 3 sig figs. The mass of sample was 4 sig figs. And we typically do not consider conversions within the metric system or molar masses of compounds as our determinations of sig figs. So the final result, therefore, here should have been 600 negative 65 kilojoules per mole to 3 sig figs. And this would be our answer, or what we'd call the molar heat of combustion. Notice that is negative because, as expected, a combustion reaction is exothermic and therefore it should put energy or heat out into the surroundings. Okay, my students, I hope that was helpful. Again, this was a practice with the technique of bomb calorimetry. Don't forget that in our studies of energy transactions during chemical reactions, we had another kind of calorimetry, which is the one similar to the one you did in lab, which had to do with using a coffee cup calorimeter. And the calculations there, although they follow the same principle of conservation of energy, they have a few things that might be a little different. Also, remember that we also studied Hess's law, and there are different applications of that. Again, if you have any questions, please don't hesitate to send me a note or come visit me in my office during your student times. Thank you so much. Have a good time.